The final topic in this unit is on something called dielectrics, which is a curious little word whose meaning will become clear as we go on. An insulator in an electric field is called a dielectric, or sometimes it's called a dielectric material. This name will have a meaning a little bit later, so hold on to that for a second, and let's walk through what we have here. We're going to talk about two parallel plate capacitors, one which is vacuum insulated, and the other which is dielectric filled. Vacuum insulator is sometimes called vacuum gapped, or really just vacuum capacitor. So here we have a plate charged positively and a plate charged negatively to plus and minus Q0 with some voltage across them, which we'll call delta VC0 across some distance d. That will have a capacitance we'll call C0 in vacuum. And of course, we remember that that capacitance is epsilon naught A over D. Does not depend on the charge, remember, or on the voltage, but relates to each other. In the dielectric filled case, we have some block of material which completely fills the space between. Later on, we might relax that a little bit, and it's not that crucial that it completely filled it, but makes things more complicated and doesn't really add much. It's not a big deal that it's larger than the capacitor, just that it fills all the space between them. And again, we have charge, and here we're gonna put the same amount of charge. So we'll have maybe charged this capacitor, disconnected it from the battery, and then slipped this material in. That might be a way to think about this. And so therefore we have a new voltage across it called delta VC, and it will turn out that the capacitance C is greater than the original capacitance C0. We'll see why the capacitance is larger in just a little bit. The electric field on our two plates, which of course is created, goes like from all the positive charges that were here and all the negative charges that were here. So the electric field would flow, of course, this way. And we know that in the vacuum case, at least, it would be uniform and fills space completely. But of course, the insulator is made of atoms. The atoms have some negative charge and some positive charge, and they're sort of trapped together. They can't move very much, although they can rearrange themselves in the atom, so that when we apply an electric field this way, the positive charges are drawn over this way, the negative charges are drawn the other way, and the atom becomes what's called polarized. All right, still neutral, right? Still net charge of 0, but the charge is no longer symmetrically distributed. There is a definite plus end and a negative end to that atom, or maybe to molecules, depending on the chemistry going on. But more or less, the idea is that we do end up getting pluses and minuses that have shifted a little bit. And then you can imagine, if you look at these things, that instead of taking this to be my atom that is neutral, which is fine, I'm going to group them this way, which I can always do, right? So let's see if we can get this to work nicely. That to there, those to there, those to there, and so on. Oops. Now I'm not doing anything physical, I'm just grouping them sort of in my mind, but you can see that I can basically form interior pairs that are still neutral. Right? And yet what I end up here is a sheet of uncompensated positive charge and a sheet of uncompensated negative charge. All right? We can represent this as two sheets of surface charge with a neutral region between them. And that surface charge creates an electric field inside the insulator. It looks like a capacitor. It looks like we've suddenly created some new capacitor over here inside our existing capacitor that is positive on this side and negative on this side, inside our actual capacitor, which was positive on this side and negative on this side. Now, again, these are inside the insulator. They can't get into the conductor. They can't actually cancel the positives and negatives that are on the capacitor's metal conducting plate, but they act to shield it in a lot of ways. Those can meet up and shield the charge, reducing the electric field. In other words, they create a new electric field inside their fake mythical capacitor that goes this way. We call that the induced electric field. All right. And Outside, of course, again, it would look like 0, just like for a regular capacitor. And the induced field is opposite to the applied field that came from the capacitor. It's the two sheets of charge, by the way, that gives us the name dielectric, right? Two electric sheets. The induced charge sheets create an induced field which acts counter to and thus weakens the original electric field. So we have the original electric field was charge density over epsilon naught. The textbook that I stole this image from used eta rather than sigma. There's no particularly good reason, so we would probably have written this as sigma naught over epsilon naught, and then sigma induced over epsilon naught. So, to get back to this, we have a capacitor which generates an electric field this way, which is its surface charge density over epsilon naught. But then we induce a field that goes this way, which is opposite to the original field. And so we can show later on it will be smaller than, it's opposite to but smaller than the original field. So it weakens the original field, makes it seem less strong. It still points the way we'd expect it, from positive to negative, yay, but is weaker than we would have thought offhand. This is just another take, just another picture of this with prettier or different colors, but nothing new going on here. Again, we have a neutral state. All the atoms are neutralized completely. We apply an electric field, and it causes a induced field back, which means the actual field we see is much less than we would have gotten from just this collection of charge. We now define the dielectric constant as the original field over the actual field that comes out. We represent it with the Greek letter kappa. This is lowercase kappa. It looks a lot like a K, but it's not a K. Most especially for lowercase, it doesn't have the little loops that go with K. It looks a lot like a shrunken uppercase K. Also, usually in handwriting, the leg comes off here, whereas if you're writing a capital K, we usually have them come from the same point here. Does any of that matter? Means be careful, all right, especially when you're doing your own handwriting so you don't confuse yourself. All right, what is the dielectric constant? The dielectric constant is essentially the factor by which the electric field is weakened. All right, it's clearly dimensionless because we have electric field over electric field, so there's no units. It will turn out to always be greater than or equal to 1. And it's intrinsic to the material. It's a feature of the material. It's quantum chemistry that's going on. It will be larger for more easily polarized materials. Things that can more easily be spread out or rearranged like that will tend to have higher kappas. By definition, the vacuum has kappa of 1. You can see that since E0 is the vacuum field and E is the actual field. If if my actual field is the vacuum field, kappa is 1. And air has kappa equal to 1 at least out to 3 decimal places. And so with 3 sig figs or less, we would say kappa is 1. If you go to 4 sig figs, I think it's like 1.0001 or something like that. So we usually treat it as 1. But it'll be important later on that it's not exactly 1. All right, let's call the voltage across the vacuum filled capacitor V0 and the voltage across the dielectric filled one V. And again, we're assuming here that they're not hooked to a battery, but it's an isolated capacitor so that there's no outside source of voltage, no outside source of charge. Well, we know that the voltage across the dielectric field capacitor is going to be just E times D. It's still uniform, so we can take E dot ds, but just take the E outside and we get E times D. But of course, E is the vacuum field over the capacitance. So now the dielectric potential is the vacuum field over the capacitance times the distance. Pull the kappa out front. We have 1 over kappa times a thing which is the vacuum field times the distance, but the vacuum field times the distance was the potential on the vacuum filled capacitor. So putting all this together, we get that the new voltage is 1 over kappa times the original voltage, just following the electric field. So inserting a dielectric here reduces the voltage. Again, we assume the capacitor is isolated so that no new charge flows, so the voltage can be reduced. If we hooked up to an EMF source like a battery, that would hold the voltage constant and something different would happen, and we'll talk about that in a little bit. All right, then we can say that, well, the capacitance is Q over V, but V is 1 over kappa times V0, so this becomes kappa times Q over V0, or kappa times the original capacitance. So we get the most important result that comes out, although we said it earlier. Inserting a dielectric increases the capacitance of the device. Inserting a dielectric allows us to store more charge for a given voltage. Why is that? Well, largely because the polarization, the sheet charges that are polarized, that are induced, are shielding some of the plate charge. So it's easier to jam more stuff onto that plate charge. Right? It's as simple as that. The plate can take more charge because it's being attracted to the induced opposite sign charge that's in the insulator. It's much the same reasoning as to why decreasing the separation increases the capacitance. We've essentially decreased separation by a lot. All right, every material has a characteristic electric field at which the dielectric fails and a spark is produced. This is called the dielectric strength of the material. What's going on here, of course, is that we started off with a negative charge, some positive charge and some negative charge trapped inside some, say, atom, and then we apply an electric field, and that produced for us an elongation, but they're still trapped. However, if I make the field really, really, really strong, I will eventually break these bonds. And then all of a sudden we get current flow. We'll get that the positive will fly off that way, and the negative will fly off that way. And we get a spark. We get some massive amount of current until the things are rebalanced. For air, that dielectric field strength is about 3 million volts per meter. So a lot. Like, it's got to be a pretty strong voltage to do that, but air will eventually break down, which is where things like lightning strikes come from. We can look over here, just some typical values from textbook. Dielectric constant for vacuum is 1, and of course it has no dielectric field strength. You can't tear the vacuum apart. Although some people doing quantum mechanics would say you are putting energy in the vacuum state, maybe you can actually pair produce. So in a very advanced class, you might end up going back and saying, hey, let's revisit this from the point of view of quantum fluctuations. Maybe you can pair produce on a vacuum and in that sense have a vacuum field strength, dielectric strength. I don't know what that value would be, but definitely way more than the 10 to the 6 volts meters we're talking about here. All right, air has, I guess, 1.006, not 1, sorry about that, and a dielectric strength of 3. Teflon has dielectric of about 2 and needs 60 million volts per meter to break. Do notice that there's no direct connection between dielectric constant and field strength. They don't scale in any easy, natural way. Allegation here is that pure water is highly polarizable but has no dielectric field strength. I find that unconvincing because I know that you can electrolyze water into hydrogen and oxygen. So I don't know what this would be, but we could probably figure it out if we really cared about it. I don't think it's really nil. I don't know why they left that out. All right, consider a capacitor with capacitance C0 in vacuum hooked up to a battery. A dielectric material is inserted in the gap while the battery remains connected. What happens to the electric field between the plates? Let's look at the most important things. We're looking, of course, for the electric field, and we're doing it under conditions which is the battery remains connected, which means that the voltage is constant. But remember that the voltage across the capacitor is just the electric field times the gap distance. This isn't changing because we haven't changed it geometrically, and this can't change because we have a battery, which means we see right away that this can't change either. It must stay the same. You might object here and say, wait a minute, we said that putting the dielectric in would weaken the electric field. And that's true, but we said that in the case where the capacitor was isolated. Since it was isolated, the charge could not change, and the polarization would generate a back field that would reduce it a little bit. On the other hand, in this case, the voltage cannot change, so the electric field cannot change. What's going on? Well, remember that we're going to have something like Q equals CV is the original amount of charge, and now we have new charge, which is the new capacitance, times the same voltage. And we can see that since the new capacitance has gone up, so has Q. Q is larger. So while the electric field for any given point particle is less, is damped a bit by having the dielectric in there, we have more charge, which compensates exactly. And so in this case, the electric field stays the same because the voltage stays the same, but the charge must increase on the plates. We draw more charge from the battery. A capacitor of vacuum capacitance C is filled with dielectric material with constant kappa. It is fully charged and then disconnected from the battery. What is it? If the dielectric is then removed from the capacitor, what happens to the energy stored in the capacitor? Now, an important thing, of course, is going to be that the battery is disconnected. So Q must stay constant and V changes. All right, the energy in the vacuum-filled capacitor, which we'll call UVac, is going to be the charge squared over twice the vacuum capacitance, which is C. And the energy in the dielectric-filled capacitor is going to be Q squared over its capacitance, which is 2 kappa C, since the capacitance is kappa times C. And then this question asks us for the vacuum one over the dielectric one. So we can see, well, the Q's are constant. That's why I picked that form. We know the Q can't change because we're disconnected from the battery. So we'll have something like Q squared over 2C over Q squared over 2 kappa C. And with all the machinations that go on there, we end up with just kappa. So the vacuum has more energy than the dielectric filled one. By the way, since we're increasing the potential energy that is stored in the capacitor, it must take work to do that, which means that it would be hard to pull the dielectric out. It wants, quote unquote, wants to stay inside the capacitor. It should be obvious to you, and you should convince yourself and walk through to convince yourself if you don't see it right away, that if we had instead left the battery hooked up, then we'd have found that the potential energy in the vacuum state would be less. That it would like to have, it would have a lower energy by having the dielectric removed, which means the dielectric will try and leave on its own. It would shoot out of this thing if we had an opportunity for it to do that.